Hello everyone. Today in this video we will study about magnetic effect of electric current. That means when an electric current passes through a conductor, it produces a magnetic field around it. That means it possesses magnetic properties. It produces magnetic field and it produces magnetic properties. Now here is the introduction for both electricity and magnetism. They are linked to each other and it is proved when electric current passes through the copper wire, it produces magnetic field. In the whole chapter, we are going to discuss many activities through which you will learn that how electricity produces magnetic effect and how magnetic field produces electricity. Okay, so before that you should know what is magnetic field. Magnetic field is that quantity which has both magnitude and direction. Direction of a magnetic field is usually taken to be the direction in which a north pole of the compass needle moves inside it. The north pole of the compass tells the direction or the north pole of the magnet. Okay. Then comes to the next one, magnetic field lines. How do we observe it? It is a convention that the field lines emerge from North Pole and merge at the South Pole. As you can see in the image there, from the North Pole all the field lines are emerging out and it is entering from South Pole. So what will happen basically inside the magnet? Inside the magnet, the nature of these magnetic field, what it would be? It would be from south to north. So inside the magnetic field lines move from south pole to north pole, but outside the magnet, it moves from north pole to the south pole. Second thing, no field lines of a magnet bar are found to cross each other. Can you see in the image? No field lines can cross each other. If it happens, then it means that at the point of intersection, if two field lines will intersect, then at the point of intersection, compass needle will point towards two directions. But how is it possible? Can a needle direct towards two directions? No, which is simply not possible. That is why two field lines cannot intersect each other. Second, last, the magnitude of the magnetic field at a given point increases with the increase of current through the wire. That means if you will increase the flow of current through the wire, it will definitely increase the magnitude of magnetic field. Clear? So magnetic field directly depends upon the flow of current. Then arrangement of iron fillings around a bar magnet. This activity is very easy. What we simply have to do, we need to keep a bar magnet on a sheet of paper. We will sprinkle some iron fillings around it. Then gently tap that paper. What will happen at last? These iron fillings will arrange themselves in such a way as shown in the figure. This will show the magnetic field lines. Actually, magnetic field lines we cannot see, but we can feel them. Or through this bar magnet, we can define how the magnetic field lines look like. When iron fillings are placed in magnetic field, they are magnetized and induce poles in them. Iron fillings, the small particles of this iron filling, when get magnetized, act as a magnet and they attract every other particle around it, and this is how they form the magnetic field lines around the bar magnet. Then comes some of the magnetic field lines properties. Direction of magnetic field is tangent to the field line at any point in space. Magnetic field line's direction is a tangent. Tangent, you know, the curve, the perpendicular drawn to the radius at the point of contact. A small compass will point in the direction of the field line. Strength of field is proportional to the closeness of lines. That means Lesser the distance between the field lines, more will be the strength of field. That means if they are very close to each other, what magnetic field lines, if they are very close to each other, we can say that the magnetic field is very strong. It is exactly proportional to the number of lines per unit area perpendicular to the lines, called the areal density. Density is related with the term dense. That means more dense the lines are, more will be the electric field. Magnetic field lines can never cross, meaning that the field is unique at any point in a space. Field, a single magnetic field line is unique at any point in a space. They cannot cross each other. If they will cross, they will show two directions, which is not possible. Magnetic field lines are continuous, forming closed loops without beginning or end. There is no beginning or end. These are the continuous loops, because as you have seen in the previous figure that it emerges out from North Pole and it enters through the South Pole. But inside the magnet it is moving from South to North. So they are forming a continuous loops. Okay. Next is an experiment, Oersted experiment. What kind of arrangement is there? A key is there, a straight wire AB, which is connected to a battery V and a key K. Wire is held horizontally over magnetic needle. How we have to place this wire? Wire is being kept horizontally on the needle, magnetic needle. When we will allow the current to pass through the conductor, what will happen? The magnetic needle will point towards the North Pole. And if we will reverse the direction of the current, again it will point, but this time it will point in the opposite direction. When key is closed, current flows in the wire in the direction as shown. Needle deflects one side. When key is taken out, current wire becomes zero. Needle returns back to its original position, that is south-north. This shows that a magnetic field is associated with an electric current. That means compass has shown the deflection when there is magnetic field around it. That means when the current was flowing through the conductor. But as soon as you will turn it off, that means the circuit is open. So what will happen? No current is flowing through the conductor. It will not generate any magnetic field. That is why the magnetic compass will not show any deflection. But when the direction of current in wire is reversed again, then again the deflection of needle is also reversed. So if direction of current be same, wire be put under the needle, direction of deflection becomes reversed. Then comes magnetic field due to a straight current carrying conductor. Now, how a straight current carrying conductor produces a magnetic field? When electric current is carried by a straight wire, as you can see, the hand is holding that wire, or in the circuit diagram, there is a wire passing through the whole of that cardboard sheet. So when electric current is carried by this straight wire, it produces magnetic field lines in the form of concentric circles. So a straight wire, say, if you will allow electric current to pass, it will produce magnetic field lines in the form of concentric circles. How does it happen? That depends upon the right hand rule. This is a figure here. So if you can see, the hand is holding that current carrying straight conductor, and this conductor is attached with ammeter, resistance, battery and a key, and of course wires. So suppose we make electric circuit using a straight copper wire. We bring iron fillings. How do we find those concentric circles? That this conductor is producing the concentric circles or concentric magnetic field lines. We bring iron fillings near it and switch on the circuit. Iron fillings arrange themselves in the form of concentric circles around copper wire. As we have seen in case of the bar magnet, these magnetic field lines are the small curves from north to south pole. But in case of this current carrying conductor, this is forming concentric circles around that conductor. This shows that magnetic field lines produced by a straight conductor is in the form of concentric circles. See here. Direction of magnetic field depends upon the flow of electric current. Now, this direction we know that if the electric current flowing will reverse, direction of the magnetic field will also reverse. As we have seen in case of the Oersted experiment, the deflection shown by the needle, magnetic compass needle, has been reversed as we have reversed the flow of electric current. So if we will bring a compass near electric circuit, if current flows from north to south, north pole of compass would deflect towards east side. If direction of current was reversed, that means now flows from south to north. So compass would show deflection towards the west side. Clear? Then it depends upon the right hand thumb rule, which will decide that in which direction the magnetic field line will go when the current is going from this to this, or north to south, south to north, whatever. So right hand thumb rule states that imagine that you are holding a current carrying conductor in your right hand such that the thumb points towards the direction of current. This is your right hand you have to use. The thumb will tell the direction of current, you know, in the circuit, because you have attached the battery. So you know that in which direction the current is flowing. Then your fingers will wrap around the conductor in the direction of field lines of the magnetic field. So the curl of this finger will tell the direction of magnetic field. It is being shown by the arrow, blue one, in the figure in the form of circle. Red arrow showing the direction of current through the conductor. So the magnetic field lines is in clockwise direction. If you will reverse it, you have to turn your thumb in upward direction. Then again the magnetic field lines will get changed. This is what the right thumb rule is. Then how you will measure the magnitude of magnetic field? This is the second thing then. Strength of magnetic field we know directly depends upon the current flowing through the conductor. So B, which is denoted, magnetic field is denoted by capital B, is directly proportional to I. Strength of magnetic field B decreases on increasing the distance of point of observation from the point. How far you are standing from that conductor, lesser field you will experience. So it inversely proportional to the distance of the point of observation. Combining the two, we get B directly proportional to I upon R. So SI unit of strength of magnetic field is Tesla, denoted by capital T. Or if you want to find with the terms, so 1 Tesla is equals to 1 Newton upon 1 ampere into 1 meter. That is Newton per meter per ampere, or Weber per meter square. Tesla is a very big unit for practical purposes. So in CGS system, 1 Tesla is equals to 10 to the power 4 Gauss. So main thing here to understand is that B is directly proportional to I and it is inversely proportional to R. Then comes magnetic field due to a current carrying circular wire. Now we have studied about the current carrying straight current carrying conductor. Now this is a current carrying circular wire. Again, what will happen at the point of observations? Magnetic field lines are the concentric circles at every point of current carrying circular loop. The direction of magnetic field of every section of the circular loop can be found by using right hand thumb rule. Now in this case also we will use the right hand thumb rule, but there will be slight changes in using that. At the center of the circular loop, magnetic field lines are straight. Circular loop के center पे the magnetic field lines are straight. Then each segment of circular loop carrying current produces magnetic field lines in the same direction within the loop. Direction of magnetic field at the center of the circular coil is perpendicular to the place of coil, that is along the axis of the coil as shown in the figure. So this is the circular loop as you can see, and the 2 points you can see the concentric circles formed by the magnetic field lines in the clockwise or in the anti-clockwise direction, which has been found with the help of right hand thumb rule. Clear? Now the next is factors affecting the strength of magnetic field. It is same, directly proportional to the current through the loop, and it is inversely proportional to the radius of the circular loop. If you will combine the two, you will get I upon R. If there are n turns in the circular coil, each turn creates magnetic field at the center. So it is not the straight one now, it is the circular and it is forming concentric circles. So there is slight change, that the greater the value of n, greater is the strength of magnetic field. So please note that the strength of magnetic field is also called as magnetic field only. B is directly proportional to n. N means the number of turns. If we will combine the 3 terms, in case of circular coil, B will be directly proportional to N, I upon R. So, till here we will do, and in the next video we will be discussing about the current carrying through or the current through a solenoid.